First question is the combination of the gates shown below yields. First part shows a NAND gate views both input terminals A I1 and I2 are connected to terminal A. The truth table for a NAND gate, we know that inputs are I1 and I2 and output is Y. For these two inputs, we have four combinations 0, 0, 0, 1, 1, 0 and 1, 1. The output will have for NAND gate as 1, 1, 1 and 0. Because both input terminals are connected with A, so both will have the same value. Either they will have a 0, 0 or it will have a 1. And this 0, 0 will occur when the terminal A have the value 0 and 1 when this terminal A has the value 1. And if terminal A has the value 0, output terminal has the value 1. And when the input terminal A has the value 1, output terminal is 0. It means this circuit shows a NOT gate. Hence, this is the NOT gate, which can be symbolically represented as triangle with a 0. Similarly, in second part, there is a NOR gate whose both input terminals say I1 and I2 are connected to terminal A. Similarly, if we draw a truth table for the NOR gate, whose input terminals are I1 and I2 and output terminal is Y, four possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. For NOR gate, because in OR gate, output is 1 when any of the input is 1, otherwise 0. For NOR gate, it inverts, that means output will be 1 when both inputs are 0, otherwise it is 0. And because both input terminals are common and connected to A, so these have the same value, either it is 0, 0 or 1, 1. And these are connected with terminal A, and this A will have either the 0 or the 1. So for 0, we have the output 1. For 1, we have output 0. That means again it is a NOT gate. So the circuit in the part B is also a NOT gate, which can be represented by the symbol of NOT gate. In C part, the first is OR gate, and it is followed by this symbol as we have shown in part A is a NOT gate. That means it is OR followed by NOT. That means we can say it is a NOR gate. In part D, again the circuit is NOT gate. Another circuit is NOT gate. So if terminal input is A, then output will be A complement. And if input is B for the NOT gate, output will be complement of B. And these two inputs are given to the NAND gate. So we will have the Y will be equal to AND of complement of A and complement of B and whole complement. This will be equal to, using the De Morgan's theorem, complement of A, and this dot symbol will changes into plus or the OR, and then again complement of B complement. And we know that complement of complement will give simply the A. So it will be equal to A or B. So the circuit represents the OR gate. Second question is, truth table for a system of gates shown in the figure is, part A shows the input terminal A and B is applied to a NOR gate, which is followed by a NOT gate. So NOR gate followed by a NOT gate is effectively a OR gate. Therefore, the truth table will be, as we have already done, if terminals inputs are 0, 0, 0, 1, 1, 0, 1, 1, then output will be 0, 1, 1, 1 for the OR gate. Second part is, there the two input A and B applied to the two NOT gates. So output of NOT gates will be the complement of A and complement of B, which is applied to the input of the NOR gate. So Y will be equal to input complement A or complement B. This is the output of OR gate, and because our gate is NOR gate, so its complement will give the output of NOR gate. So using the De Morgan's theorem, which says complement of A or B will be equal to complement A and complement of B. This symbol plus changes to dot. So we will have complement of A dot complement of B. So also we know that complement of A will be the A itself, so it will be the A and B. So it is a AND gate, and the truth table for the AND gate, which we have already done, is if inputs are 0 0 0 1 1 0 1 1, then output will be 0 0 0 1. That means high when both the input terminals are high. Part C is the two inputs are A and B applied to a OR gate. So its output will be A or B. And this A or B output and another is input A applied to a NAND gate. So output of NAND gate will be equal to the AND of two input, that is A and A or B, and its complement. So on solving using the De Morgan's theorem, we will have A complement or A or B complement. This will be equal to, again applying the De Morgan's theorem, it will be complement A dot complement B. So further we can write it as, because we know that A and 1 will be equal to A, and we have complement A dot 1 plus complement A dot B bar. So we can further write it as complement of A 1 or B bar, taking this A common from the both the terms. So it will be equal to this 1 or B bar. We know that A or 1 will always be 1, because in OR gate any of the terminals should be high, then output terminal will be high. So in this OR of 1 and B bar, we will always have the output 1. So we will have complement of A dot 1. And because using the expression which is A dot 1, that means if we take the AND of the two terminals in which one of is high, then the output will be other input. If other input is 0, output will be 0. If other input is 1, then output will be 1. So we finally have complement of A. So it is the complement of A. Therefore, the truth table will be AB 0 0 0 1 1 0 1 1. These are the two inputs, and output Y will be the complement of A. It is independent of B. So if input is 0, output will be 1. If input is 0, again it is 1. And when A is 1 1, the output will be 0 0. This is the truth table for the part C. Similarly, the we have the part D, in which we have the four NAND gates which are connected, and this is the actually the circuit of the exclusive OR gate. In exclusive OR gate, the Boolean expression is Y is equal to A B bar plus, that means OR A bar B, and its truth table will be A B Y. Four combinations are 0 0 0 1 1 0 1 1, and output will be, in exclusive OR, output will be high when any of the one of the term input is high. So Y will be 0 1 1 0. This is the truth table for the part D. This expression for the Y equal to AB bar plus or A bar B, we can also evaluate it. Here, suppose this is A and B. So output of the NAND gate is, this is the first NAND gate, this is second, this is third, this is fourth. So for the output of first NAND gate will be A and B complement. Then this is also input of the NAND 2, and another input is A. So output of NAND 2 will be A and complement of A and B and this whole complement. Similarly, output of the Third NAND gate will be B, because this is B, and A and B complement whole complement. And now these two inputs are applied to the NAND gate 4, and we have finally the output Y, which is the AND of A and B complement, and then AND another input is B and A B complement, and because it's a NAND gate, it's whole complement. Now on simplifying using the concept that De Morgan's theorem, that is A and B complement will be equal to A complement or B complement. So we will write it is A and AB complement and then complement. This is the complement which we are removing. Or it is B and AB complement, then complement and complement. Again, using the property that double complement of A will also gives A. So we will further have these two complements will be neutralized, and we will have further A and AB complement or B and AB complement. This will be equal to, again using the De Morgan's theorem for this AB bar or AB complement, we will have A and complement A or complement B, or B and complement A or complement B. Now opening the bracket, we will have A and A bar or A and B bar plus, that is, or B and A bar or B and B bar. Using the property that A and A bar, if A is 0, A bar is 1, and if we take the AND, it will be 0. If A is 1, complement will be 0. Again we will take the AND, it will again 0. So A and A complement will be 0. Or A and B bar or B A bar, B and A bar, or, and this B dot B bar again it is 0. And we know that property is 0 or A will be A. That means it will be A and B bar or B and A bar. This is the output of the exclusive OR gate. Third question is, the correct Boolean operation represented by the circuit diagram drawn is, there are the two parts. In one part, we have a circuit having the LED connected with resistor and a battery through the two switches A and B. These two switches A and B have the two positions, 0 or 1, 0 for the open switch and 1 for closed switch. So for the two switches A and B, they are the four states: 0 0 when both switches are open, 0 1 when switch A is open and switch B is closed. In third situation, A is closed and B is open, and in the fourth case, both A and B are closed. Then the position of the LED, that means either it is a glow or do not glow, will give our output. Here we can see that when both are open, then there is a potential difference between the LED and it will grow. So we can say that when 0 0, output will be 1. And when one of the switch is closed, again the circuit through the switches is open, and again there is no current in this part. Therefore again we will have the high or the LED will glow. But in case when the both switches becomes closed, this is closed, in that case the path through these switches is a short circuit, and in short circuit the total current flow through the this short circuit path, and the voltage across LED will be 0 and it will not glow. That means we can say output is 0. And this is the case of the NAND gate. In NAND gate, when both input are high, output is 0 else 1. So part A shows the NAND gate. Part B is, there are the two inputs A and B which are applied to the two diodes, junction diodes D1 and D2. The combinations of two inputs are 0, 0, 0, 1, 1, 0, 1, 1. Means voltage at the terminal A and B may be 0, that is low voltage or 0 voltage, or it may be 1, that means high voltage or 5 volt. Then we have to find the output voltage. If any of the voltage is high, then in that case diode will conduct and drop across the diode will be approximately 0. So total voltage appears at the C. That means we will get the high voltage at the terminal C. So if both the inputs are low, there is no conduction in the diode, so no output at the terminal C. That means output will be 0. And if any one is high, that means we will have the high voltage. So we can say it is a OR gate. Fourth question is, the figure shows a logic circuit with two inputs A and B and output C. The voltage wave forms across the A, B and C are given. The logic circuit gate is. Here the inputs are A and B and output is C. So for two input we have four combinations 0, 0, 0, 1, 1, 0, 1, 1. Now we see that in 0 to T1 input A is low, input B is also low and output C is also low. So for 0, 0 output C is 0. Then for T1 to T2 input A is high, input B is low and output is high. So we can say that 1, 0 has the value of output as 1. In T2 to T3 input is 1, that is high, input B is also high and output is also high. So for 1, 1 output is again high. In T3 to T4 input A is low, input B is high, output C will be high as shown in the diagram. Therefore for 0, 1 we will have again 1. So it complete our truth table. Again we can see further the values given for T4 to T5, again it is 0, for B 0 and C 0, which is similar to for input 0, 0 and output 0. For T5 to T6 input is 1, output is input B is 0 and output is 1. So 1, 0 is 1, it is again verified. Then last case it is 0, 1 and output is 1. For 0, 1 output is 1. So it complete our truth table. So as per truth table, output is high when any of the input is high and 0 when both the inputs are 0. So it is the OR gate. Fifth question is, in the combination of the following gates, the output Y can be written in terms of the inputs A and B as. Options are A dot B bar, A dot B bar plus A bar dot B, A dot B whole bar plus A dot B, A plus B whole bar. Here dot represents AND gate, plus represents OR gate, and the complement is represented by the bar over the letter. This is the complement or NOT gate. In the diagram, input terminal A is applied to the gate, which is the AND gate. This is the AND gate 1 and another is AND gate 2 and this is the OR gate 3. So for AND gate 1, two inputs are, one is A, another is B, which is applied to the NOT gate, and output of NOT gate will be complement of B. So the input of AND gate are A and B complement, so output will be A and B complement. Similarly, when A applied to the NOT gate, its output will be complement of A, and when we see the AND gate 2, they are the two inputs complement of A and B, so we will have complement of A and B. This is the output of the second gate, which is the AND gate. Now these two inputs are applied to the OR gate, which is the gate number 3, and we have the output Y. This Y will be equal to one of the input, this is the A and B complement, or and then another input, that is the complement A and B. And actually this is the exclusive OR gate. And in the given options, option B is the correct option. To get output 1 at R for the given logic circuit, the input value must be, options are x equal to 0, y equal to 0, x equal to 1 and y equal to 0, x equal to 1, y equal to 1, and option D is x equal to 0 and y equal to 1. If we see the diagram, input values are x and y. X is applied to a NOT gate, so output is x bar, and another input to the OR gate 1 is y, so output will be x bar or y. Similarly, if we see the NAND gate 2, inputs are, one is the x and another is the complement of y. So the output of the NAND gate 2 will be x and y complement complement. This will be equal to, using the De Morgan's theorem, complement of x or double complement of y. This will be equal to complement of x or y. And these two inputs are applied to a NOR gate. So output of NOR gate R will be equal to input P or Q and its complement. And input P is complement of x or y, or another is again complement x or y and its whole complement. And because these two are same, so if we take the OR of the same input, we will have the same value A. Therefore, it will be complement of A or Y complement. So this can be written as, using the De Morgan's theorem, double complement of X or is converted to dot, that is and then Y complement. And this X double complement will be simply X and Y complement. Now if we check the given options, if X equal to 0 and Y is also equal to 0, then complement of Y is 1 and its AND will be 0. So it is not desired. In option B, if X is 1 and Y is 0, then complement is 1 and 1 and 1 will be 1. So it is a desired option. We can also check option C and D. In C, X is 1 and complement of Y is 0, its AND will be 0. So it is not acceptable. And in option 4, X is 0 and complement of Y is again 0 and it is also give the 0. So it is not acceptable. So option B is the correct option.